In this video, I'm going to describe how to design an anti-surge system for a centrifugal compressor that protects against surging on fast stops. So I'm not going to describe what a surge is on a centrifugal compressor. I'm not going to talk about controlling for surge avoidance in continuous operation. I'm just addressing the problem of a fast stop of the machine and equalizing the pressures around the compressor fast enough to avoid a compressor surge. It's a pretty tricky problem. Things happen very fast, and there's some tricky things to try to describe in the simulation. So we're looking at a schematic of a turbine-driven centrifugal compressor. This is from a OEM vendor's drawing for a surge control system. And I just want to quickly walk through the schematic. So on the left, we have suction and loading valve, a suction scrubber, a flow meter, a turbine-driven centrifugal compressor with temperatures and pressure instruments, a discharge check valve, a gas cooler, and this is sort of an unusual thing to put here. Normally you wouldn't have that. Just a discharge check out here is more typical. A recycle loop through an anti-surge valve. So a positioned valve could be a ball valve, could be a globe valve. In this case, it's a globe valve. And then a vent and a discharge block valve. So really all we're concerned about in the fast stop modeling is basically the performance of the turbine and compressor, the volumes of the discharge, the performance of the surge control valve, and also the volume of the suction, I should mention. So that's a very simple schematic. And the goal of designing a good system is to avoid crossing the surge line on the performance map of the compressor. So we're looking at a head flow map here, an operating point shown, and the vendor's prediction of performance of the compressor in head versus flow format. So this is pretty useful for describing performance of centrifugal compressors and holds up with changes in gas density and so on to a degree. What we want to avoid is operating near or to the left of the predicted surge curve, which is this red curve on the left of the map. So the crosshairs indicate our current operating point. So when the unit has a fast stop, the driver power diminishes very rapidly. And if pressure ratio does not change, then head won't change, and this operating point is going to go to the left very rapidly. So it's a race of dropping the pressure ratio in the head faster than the flow is diminishing from loss of power. That's the trick for the fast stop design. So back to the schematic. So the turbine is losing power quickly, and we need to do something to get rid of this pressure ratio in a matter of seconds. So in this design, we only have an anti-surge valve. It's got to move gas from the discharge to the suction to equalize the pressure around the compressor. We're usually looking at pretty significant discharge volume with a cooler, and it's a lot to ask a single valve to move all those molecules of gas back to suction. So in the analysis, we need to know the discharge volume, need to know the flow capacity of the valve, we need to know the head flow performance map of the compressor. The other thing we have to know is the inertias of the power turbine and compressor, and if there's a gearbox, that as well. So that is going to play into how fast the flow is diminishing with decreasing power. Suction volume. We might also want to model that, but the safest thing to do is to assume that suction pressure is constant. And that's a worst case scenario, because if you think about moving these molecules to the suction, you'd think the pressure would go up. And it depends on the volume and what other elements are upstream of the compressor. Usually it does go up a bit during a fast stop, but if you assume it stays constant, that's holding the suction pressure lower than reality by a little bit and making your analysis a bit more conservative. So this is the simple anti-surge valve only design, and it's pretty tricky to make a unit not surge with just an anti-surge valve. Many years, many compressors designed with this arrangement, and most of them surge on fast stops. How big a deal is that? Usually not a big deal. You'll see some vibration maybe some seal wear, but usually not a terrible thing. I personally would not design a system to surge every time it fast stops. I think that's a bad design practice. You're taking a lot of risk with durability in the machine. And if things get bad enough, this compressor could actually spin backwards on a fast stop. I've seen that a couple of times, and that definitely causes damage. So as a designer, I would not cross my fingers and design a system to surge on every fast stop and hope it doesn't damage the machine. So how would we arrange this in a way to reduce risk of surging on the fast stops? Well, we could implement another valve called a fast stop valve in parallel with the anti-surge valve, so the FSV and the ASV. It's shown as a position valve in the schematic, but actually it's just a on-off discrete control valve. And the benefit of doing this is that you could put in a much larger flow capacity valve here and optimize your surge control valve for good control in steady state. The downside of this arrangement is that you're still dealing with a really large discharge volume. You've got a lot of gas to move back to suction, and you're going to have large pipe sizes to keep the velocities reasonable through this recycled network. So this was used frequently, maybe in the aughts on to maybe 2010-ish. This design had been used forever, up until people realized that fast stop surging is a common problem. So this was a step toward improving things, but the best solution, I think, is to implement a hot bypass valve. So again, two valves. You've got your anti-surge from downstream of the gas cooler. We also have a hot bypass valve before the cooler. That's why it's called a hot bypass. And it isolates from the cooler volume with a discharge check valve. So the beauty of this design is the volume between the compressor and this check is quite small. The volume of the cooler is usually the biggest volume in the discharge system. So you can have a quite small discharge volume, and it doesn't take a very big valve then to equalize the compressor quickly. And with a smaller valve, it opens faster. It's hard to open a very big valve quickly. So this design is really the best way, in my opinion, to avoid surging on fast stops. Downside is you've got to put a check valve in. You've got some additional piping, of course, another valve. But when you're talking about, you know, $2 million repair and a lot of downtime to fix a broken compressor, and we're talking impellers moving on shafts, seals wearing prematurely, and so on, this isn't that big of an investment in a new project. So that's the basics of the flow diagram and what we're trying to accomplish with these valves. Now let's talk about doing the analysis and sizing these valves. So that's where things really get entertaining. So again, we need to quantify the gas turbine. How fast does power decay? How fast does power begin to decay and the rate of decay? That's something that a lot of designers don't really understand and know how to quantify. It's tricky. So how would you know what to do? Well, what I do is I look at fast stop data from machines I've worked on in the field. So I have high-speed trends, and I look at the decay of power turbine inlet air pressure. So in the case of these typical turbines I work on, I'm looking at compressor discharge pressure from the gas producer. I don't have the data of the air pressure at the inlet of the power turbine, but the combustor inlet pressure, the PCD, is pretty representative. So I look at the decay of PCD in time, and that's how I develop my models for rate of decay of power. Is that important? Absolutely. That's one of the biggest variables in quantifying how quickly the machine is slowing down and how quickly the flow is diminishing. The next piece of the puzzle is the inertia of the power turbine and compressor and gearbox. So where would you get that? A torsional analysis is usually where you can turn up that information. If you don't have it, well, you can look at similar machines that you've worked on in the past and fudge some numbers. But really nice to have the correct inertia. What is the inertia doing? Well, the bigger the inertia, the slower the machine is going to slow down with a given power delta. So the turbine power is diminishing. The compressor power is a function of its speed, the flow, and the head. So the turbine power summed with the compressor power results in a negative torque. That negative torque then acts on the inertia to slow the rotor down. And in the next time step, you would then predict flow from the head and the speed. So the inertia is a pretty important variable for describing how quickly the speed is decaying and then the flow is decaying. Next piece of the puzzle is the performance map of the compressor, the head flow map. So you can make those predictions of flow given speed and head. So that's this map here. That's usually fairly easy to get from the OEM, and usually the customer is going to have a copy of that somewhere. Next piece of the puzzle is the discharge volume. So in this case, we would have a hot discharge volume and a cool discharge volume. That usually involves getting isometric drawings or walking down the piping, measuring things, and calculating those volumes. Cooler volume can be a bit tricky. Sometimes you need the dimensional drawing from the cooler, count the tubes, get the diameters, estimate the header volumes, and so on. Next pieces of the puzzle are characterizing these valves. So if you're designing the system from scratch, you don't know what these valves are yet, so you're going to make some assumptions. Hot bypass valve, we would pick a quick opening trim, and you would make a guess at a CV, a flow coefficient, and a choke coefficient. I use the ISA flow valve, ISA valve flow equations. They're available on the web to model my valves. I also input a time delay to begin opening and then a time constant to open to 63.2%. So I describe how quickly the valve is moving, and then I use the CV curves depending on the trim type to model how much flow capacity the valve has. You need pipe diameters, so there's going to be some pressure drops across the pipes. So those arguments or those inputs are necessary for the surge and the hot bypass. How much velocity are you willing to accept in the few seconds that this is moving gas from discharge to suction? For the anti-surge, my go-to is about 300 feet per second. I find that reasonable pressure drop through the piping versus the valve. And by the way, how am I calculating pressure drop across this piping? That is a tricky problem. Really, I ought to be doing CFD. But if I keep the velocities low, I can get away with using just standard pipe flow equations using assumed roughness and just a textbook pipe pressure drop formulas. On the hot bypass, I'll let the velocity get up a little bit higher just because there's some risk that the unit could run continuously at full power with the anti-surge wide open. That's not the case with the hot bypass. It's only going to open when the fast stop is initiated and stay open as the machine's shutting down. So we only have a few seconds of high velocity. I'll try to keep the velocity below 500 feet per second in the hot bypass loop. So that's how I'll size the pipe sizes. Okay, now how do I do this fast stop model? Well, I basically wrote my own software to do it. So I wrote a program in Visual Studio C# using RefProp from National Institute of Standards to model the gas, both the densities, enthalpies, and the transport properties like viscosity. So a lot to look at on the screen. Up at the upper left, just some basic system setups, elevation, how long I'll run the simulation, the inertia. So I got that from the torsional analysis. Here's modeling the turbine, the fuel shutoff delay, and the power decay. Then the hot volume and the cool volume. Then the two valves. So the anti-surge valve shown first, pipe diameters. So this is a trick to model the pressure drop across this combination of pipes and a valve. you need to solve for the intermediate pressures upstream and downstream of the valve. So it's an iterative solution, iterating on flow rate, solving for pressures through the system, and keeping it up until you converge on equal flow in this section of pipe and the valve and the downstream pipe. So iterating on these two pressures, upstream and downstream of the valve. So the valve and pipe setup shown here, we've got an inlet pipe. It's a 8-inch heavy wall, half-inch thick wall pipe. Assume a valve size, length of a pipe, number of elbows, valve flow coefficient, choke coefficient, and here's the time constant and time delay, modeling how this valve opens in time. This thing here is what I use to describe the CV versus position curve for an equal percentage valve. The higher the number is, the steeper the curve is. Outlet pipe diameter, so it's using a 12-inch heavy wall or extra heavy pipe, half-inch thick wall, 10-foot long with 1 elbow. So that's the entire anti-surge valve and pipe system. Here's the results for that system. Upstream temperature and pressure. There's the velocity upstream. Valve upstream pressure. So that's the valve pressure right at the valve. So we've lost, what is that? 16.4 psi across the piping. Downstream pressure from the valve, 308, and outlet pipe pressure, 300. Outlet pipe velocity. So this is the highest velocity in the system where the pressure is the lowest. So the density given the mass flow, calculate the velocity, and it's lower than 300 feet per second with this arrangement. And there's our mass flow. So if I change the CV, you can see the velocities and the mass flow changing. So how do I pick this CV? Well, what I do is I look at the compressor head flow map, and this curve here shows the full open flow capacity in terms of ACFM versus head for that valve. And what I want to do is I want to lay this line on the right-hand side of the compressor map. Why? I don't want to overload the compressor. I don't want to move it way out to the right where it would possibly damage the compressor during full power operation at wide open valve position. And I want to keep it well away from the surge curve. I mean, obviously it has to be to the right of the surge curve, otherwise it wouldn't work as a surge control valve. I also want to be able to run this machine with full power and not enough head to break through the discharge check in parallel operation with other units. So I want a lot of flow capacity, but not enough to overload the compressor. So I'll iterate on the valve CV until I see the valve full open curve lay on the right-hand side of the head flow map, and that's pretty ideal. I will iteratively change the piping diameters to achieve the velocities that meet my design criteria. So I might have to, increase the CV, but I see the velocities get too high, and then I'll increase the pipe sizes. So that's all it takes to design an optimal anti-surge valve, as simple as that. I don't have to worry about the fast stop because the hot bypass valve is taking care of that problem. Equal percentage trim, and there's my CV versus trim curve. Hot bypass, it's going to be a little bit trickier. This is more trial and error with running the simulation. So I'm going to have to start running the simulation and predicting how the system responds and iterating on CV and then pipe sizes to get the velocities. First, let's assume I didn't have a hot bypass valve. Let's look what happens there. So I'm going to set the CV to 0. So no hot bypass valve and just an optimally designed anti-surge valve. I'm going to run the simulation, and it didn't take long. The result was race straight into a surge. So in a trend plot, it looks like this. In 2 seconds, the machine has surged. So negative 18 surge margin. Speed was going down, pressure was starting to go down. Here's the valve flow through the ASV. It's just not moving the gas fast enough out of the discharge to keep up with how quickly the unit's decelerating and flow is diminishing. So it was just terrible. The machine went into a hard surge. That's often what happens with machines that are designed the old way with just an anti-surge valve. Could we accomplish surge avoidance with just an ASV? Well, let's see what it would take. Maybe we'll increase that CV to 800. Now the velocities are too high, so I'll increase the pipe size. Let's say 16-inch pipe. Yeah, that looks good. And let's go 12-inch on the upstream. Yeah, that looks okay. So what does that look like on the compressor curve? Well, there's the full open valve flow capacity. It's way off the head flow curve. So we're going to overload this compressor if the unit ever operates at full power with the anti-surge wide open. So not a great situation. Now let's see if it managed to keep the unit from surging. Not quite. It still wasn't big enough to keep the unit from surging. So you can see what a problem it is to just work with an anti-surge valve only. You've got a valve that's not good for the compressor, not great for control, a really big valve that's hard to open quickly, and we're still fighting surging the machine. At least we knocked some head off before it surged, but still predicting a surge. In a trend plot, it surged at about 3 seconds. It surged. So there's speed coming down, pressure coming down, and so on. So let's go back to the optimal CV and pipe sizes, whatever that was, 6.5, 1.75. And let's choose a CV of 400 again on the hot bypass. And we achieve decent velocities, actually quite good velocities with the pipe sizes I've chosen. So now we're going to run that analysis again. This is a quick open valve with pretty quick opening as well in the time constants and valve delay. Why do I think I can get away with that? A 400 CV valve is a ball valve. That's going to be, like you could do that with a 3-inch valve. So easy to get that valve open in a hurry. Whereas a 6-inch valve or even an 8-inch valve, those are harder to open very fast. So let's run this analysis with the hot bypass arrangement. That's what we want to see. So the valve opened fast enough to avoid much of a decay in surge margin. That small, quick opening valve immediately started moving gas from discharge to suction. With that small volume, that 50 cubic foot volume on the discharge of the machine in the hot section, it was having no trouble at all dropping head faster than flow would have been going down. So with head dropping off so quickly, flow actually goes up. So the machine is decelerating and depowering, but with the head dropping so quickly, it actually flows in an increasing trend. So the trend plot, really looking great. Just a little bit of a decay. Here's the flow through the hot bypass with that quick open trim and that short time constant. It's really moving some gas in a hurry. Here's the ASV moving some gas more slowly. Here's the hot discharge pressure breaking away from the cool discharge pressure. So this happened because we consumed all the compressor flow in the hot bypass. The discharge check went closed and the hot pressure diminished quite quickly. So that is a crash course in how to design an anti-surge system on a centrifugal compressor for fast stops. And I actually do this for a living. If you think I might be able to help you evaluate your new machine or in-service machine, contact me through my website. Thank you.